Hey everyone, this is actually one of the last few videos about differentiation rules and techniques because I'll be going through implicit differentiation, and it's actually only catered to the H2 students because it's only in their syllabus. Therefore, for those O-level students, do not worry about this, although if you're here, well, good on you for learning more. Implicit differentiation allows us to actually find our derivative in terms of both x and y, so we're not just limited to just one variable. So for instance, we are used to having dy dx in terms of just x. Now we can have dy dx in terms of a function in both x and y. This is actually important because for functions that are not, strictly y equals to fx, so let's say we have functions that are like this, instead we can have functions that are like this. Okay, and this makes it actually harder for us to actually obtain a derivative in terms of just one variable, and that is where implicit differentiation comes in. For example, we have xy minus y cubed equals to, let's say, sine x, or sine y rather, make it slightly tougher and actually proving my point. And first thing first is, how do you get the derivative? Okay, don't worry, let's go back to the earlier examples used in earlier videos. We have actually been doing implicit differentiation all along. Y equals to fx, then we talk about differentiation, we talk about derivative is just immediately f prime x. What we've actually done is we actually skipped a step. Alright, it's actually rather redundant, but we'll actually prove so without what I'm going to say. So we put the operator d dx on both sides, which means we're going to differentiate both sides by x. On the right side, we know it's going to be f prime x, so we differentiate fx, differentiate, you get f prime, differentiate x inside, you get 1. D dxy, differentiate y, so comparing the change of y to the change of x, and therefore you'll get back dy dx. This is actually important because this is you're going to use this a lot in our implicit differentiation, as you see later on. So the question here is, let's find a function or find the expression in terms of, for dy dx in terms of both x and y. So obviously, since you're finding dy dx, we will differentiate with respect to x. So dy dx, sorry, d dx, this is y cubed, whoops. Then d dx sine y. Okay, let's do the right one first, since it's easier. All your differentiation rules, including trigger, logarithm, exponential, will stay the same. So sine becomes cosine y. Differentiate inside, same thing. Differentiate inside, but now it's differentiate with respect to x. Therefore, y differentiated with respect to x will give me back dy dx. Left side, x, y, product rule, same thing. Differentiate x with respect to y, I get back 1, then I get back y. 1 times y is y. Plus sign, cause it's the product rule. Now I differentiate y with respect to x, I get back dy dx, and of course I times the x. Power rule, same thing. Bring down the power to the front, reduce the power by 1, differentiate inside dy dx. Simplifying, I then have y over cosine y plus 3y squared. Obviously I skipped some steps, but you end up with this expression. Another example. So we're not just limited to dy dx, we can also find dx dy. So let's just say we have y over x equals to ey cosine x. Okay, let's say we, instead of finding dy dx, we find dx dy. In terms of, again, there's no clear function of x equals to fy, therefore our derivative is likely to be both in x and y. Quotient rule, same thing. So you're going to differentiate with respect to y, and as such, differentiate y with respect to dy. With respect to y, you get back 1 times x. Quotient rule, so minus sign. Now you differentiate x with respect to dy, so you get back dx dy. Then denominator square. Simple. Now we have the product rule. Okay, differentiating with respect to y. So ey differentiate with respect to y, we get back ey, so we get back cosine x. So yeah, same thing. Plus sign, because we're doing the product rule, although if you actually look far enough, realize this will become a minus sign very soon. differentiate cosine x with respect to y, I get back minus sine x dx dy. Because I have to differentiate inside x with respect to y, I get back dx dy. Thereafter, I will simplify. There are actually two ways to do it. I'll show you the first way, which probably most of you will do it. 1 over x minus ey, we're going to do it slow, okay, equals to y over x squared dx dy minus away ey sine x dx dy. Then I then have dx dy equals to 1 over x minus ey cosine x over y over x squared minus ey sine x. And therefore, simplifying again, times x squared on both the numerator and denominator, I'll get back x minus x squared ey cosine x over y minus x squared ey sine x. So this is one of the solution. Another solution is that you notice that this is basically y over x, as you can see from here. Therefore, I can have x minus y dx over dy x squared equals to y over x plus, sorry, he'll be minus ey sine x dx dy, and you just manipulate and then you get somewhere. All right, and this is basically implicit differentiation.